Counting is quite literally as easy as 1, 2, 3. Well, it's super easy until we run out of digits. Hey, no problem. Just keep adding more symbols. Okay. Maybe a unique symbol for every quantity gets out of hand pretty quickly. Well, we can instead also count how many times we exhausted our digits, and then count how many times we exhaust both digits, and we can keep repeating this forever, adding digit after digit to count exponentially further. But what happens after forever? What if we exhaust all finite strings of digits? Do we just add a new digit at the infinite place? Yes. You can then keep counting past this number. And once you exhaust all finite strings of digits again, you increment that infinite place digit. Again, we can keep repeating this. Do it 10 times, and you can add another digit after the infinite digit. Now we can keep making infinite leaps and bounds until we exhaust all finite extensions past the infinite place. Then what? Add a new digit at an infinite places after the infinite place, of course. If you're patient enough, you can add set after set of infinitely many digits. Does it end there? No! You can then add a new digit after all the infinitely many infinite chunks of digits. Okay. I think you get the idea. If you can wrap your head around all of the infinities, this might seem simple enough. But our intuition of the infinite is awful. Personally, it's all just Greek to me. Remember the fun debate everyone had between the real numbers 0.9 repeating and 1.0 repeating? Well, how about comparing infinitely many 9s with 1 followed by infinitely many zeros? Well, it turns out they're equal. Makes sense, you say? Well, how about infinitely many 1-2s versus 1 and then infinitely many zeros? Well, they're equal too. It turns out that every number, finite or infinite, can be written as an infinite decimal expansion where only finitely many of the digits are non-zero. Going to and beyond infinity through counting leads to the world of ordinals. As the name suggests, ordinals are defined by ordering. For example, 0 is the smallest ordinal. 5 is the smallest ordinal that is bigger than 0, 1, 2, 3, and 4. 100 is the smallest ordinal that is bigger than all two-digit ordinals. We get to the infinite right away with omega, the smallest ordinal that is bigger than all finite ordinals. The smallest ordinal that is bigger than omega is what we call omega plus 1. We can then define omega plus omega to be the smallest ordinal bigger than omega plus any finite ordinal. Then we can define omega times omega, which is the smallest ordinal bigger than omega, omega plus omega, omega plus omega plus omega, and so on. Now that we're all somewhat acquainted with ordinals, what's this deal about all ordinals being representable with only finitely many decimal digits? If we want to make sense of my claim, we need to make sense of my notation first. In the land of the finite, it's pretty straightforward what a decimal expansion means. If a digit d is in the e'th position, then the digit contributes a 10 to the e times d to the decimal expansion. If there's a digit in an infinite place, then we just need to make it work in the same way. Ordinals are designed for counting, so we can enumerate the infinite decimal positions with ordinals as well. Of course, in order to make this make sense, we need to make sense of some ordinal arithmetic. Let's start with addition. In fact, let's start with addition by 1. This is pretty difficult to do without defining what an ordinal is in the first place. Instead of defining ordinals as order isomorphism classes of well-ordered sets, let's just work with these two fundamental properties of ordinals. There's always a bigger ordinal, and they are well-ordered. Whenever there is an ordinal with a certain property, there is a least ordinal with the same property. Now we can define addition by 1. Indeed, for any ordinal alpha, the first property of ordinals ensures that there is a larger one. Therefore, using the second property, there must be a minimum ordinal larger than alpha. We take this minimum to be alpha plus 1. Alpha plus 1 is also called the successor of alpha. Now that we can add by 1, how can we add by more? Well, we do it by just repeating addition by 1. Given that we can add by 1, we can add by 2. Since 2 is the successor of 1, we just take alpha plus 2 to be the successor of alpha plus 1. In general, whenever lambda is the successor of some ordinal beta, then we can add by lambda by first adding by beta and then taking its successor. But what if lambda is not the successor of any ordinal? For example, the first infinite ordinal omega is defined to be the smallest ordinal that is larger than every finite ordinal. The only ordinals that are smaller than omega, by definition, are finite, but the successor of every finite ordinal is going to be finite again. Therefore, omega is not the successor of anything. Such an ordinal is called a limit ordinal, because it is obtained by taking a limit of the smaller ordinals. So what do we do if we want to add by a limit ordinal? Well, we don't have much choice, so we just define it to be a limit of all the smaller additions. In other words, we just define the sum to be the smallest ordinal that's larger than all of the smaller sums. The idea of taking the smallest ordinal bigger than a bunch of other ordinals is very common, so it has its own special name, the supremum. Given a bounded set S of ordinals, the supremum of S is defined to be the least ordinal that is bigger than everything in S. Et voila! A completely defined procedure for addition. Now that we have addition, we can define multiplication in the same way. First, multiplication by 0 is easy. It should just be 0. Supposing we know how to multiply by some ordinal beta, then we can multiply by its successor by just doing some arithmetic. Finally, if lambda is a limit ordinal, then multiplication by lambda should just be a limit of multiplication by smaller ordinals. The final ingredient for decimal expansions is exponentiation, which is given as follows. First, alpha to the 0 is just 1. If we can raise to the power of some beta, then we can also raise to its successor just using some inspiration from the natural numbers. And just like before, if lambda is a limit ordinal, then raising to the power of lambda is just the supremum of raising to the power of everything smaller. We now have enough language to state my big claim. Every ordinal alpha can be written uniquely as a finite sum of digits in base 10. For example, you can check that omega times 25 plus 309 is equal to the expansion 25 followed by infinitely many zeros and then ending with 309. There's nothing special about the number 10 here. You can replace it with any base, even an infinite one. If you expand an ordinal in base omega, you get what's called Cantor normal form. In order to understand the approach to proving this claim, think about how you would write a number n in base 3. First, we find the largest exponent e such that 3 to the e is at most n. Then, we compute the division of n by 3 to the e and get its remainder. The quotient d is the leading digit in base 3 of n, and the remainder is what we repeat this process on to get subsequent digits. It's a good idea to review this algorithm with concrete examples yourself, so that the infinite case doesn't feel so overwhelming. Luckily for you, you can learn or review expansions and arbitrary bases with this video's sponsor, Brilliant. Brilliant is the perfect place to establish and develop your skills in maths and programming, as well as the hot topics nowadays like data analysis and artificial intelligence. Like every mathematician ever will tell you, the best way to learn math is to just do it, solve problems, and learn from your mistakes. Brilliant provides you with numerous hands-on and interactive lessons for you to achieve just that in a broad range of topics. They even have lessons on the nuances of infinity. As you can probably guess, I'm about as purely mathematical as it gets. But thanks to Brilliant, I can get my feet wet in completely alien topics to me, such as evaluating and interpreting multivariate data models. Too long have I sat through graduate colloquium talks from statisticians with no clue what they're talking about. If you want to strengthen your mathematical foundations, or explore interests in fields you have absolutely no footing in, Brilliant can come up with a plan that suits you best. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/gsheaf or click on the link in the description below. You'll also get 20% off an annual premium subscription. Thank you so much to Brilliant for sponsoring this video. But gee, I hear you say, it's much faster to perform long division by 3. Then the remainders will spit off the digits from right to left. You're correct, but only for finite ordinals. Let's say we wanted to find the smallest digit of omega, and we do so by dividing by 10. Well, it turns out that omega is divisible by 10. It's actually divisible by all finite numbers, and long division tells us that the quotient of omega by 10 is, well, omega. Since the quotient is not smaller in this case, continuing from here recursively is a lot harder to make sense of. I'm not saying it's impossible, but I don't want to get into it. If we go with the first algorithm, our task now is clear. We just need to do the same thing, except we divide by 10 and we allow the numbers to be possibly infinite. To warm up, let's first just prove that we can do subtraction. The strategy for this proof is simple. What we do is we define a set D to be the set of all ordinals that are smaller than what the difference should be. This set is bounded, by alpha for example, so we can take delta to be the supremum of D. All that's left to do now is show that beta plus delta is just alpha again. First, let's just see that beta plus delta has to be at least as large as alpha. If beta plus delta were strictly smaller, then that would mean that beta plus the successor of delta is also less than alpha, and therefore that delta plus 1 is in D, but this contradicts how delta is supposed to be the supremum of D. Therefore, beta plus delta has to be at least as large as alpha. Now let's see that beta plus delta is also at most alpha. To do this, we need to consider two cases. If delta is a successor of some ordinal xi, then xi must be in D. However, since xi is not the maximum of D, xi plus 1 should also be in D. Now of course, xi plus 1 is just delta, so this means delta is in D, and therefore beta plus delta is at most alpha. Now if delta is a limit ordinal, then the sum beta plus delta is by definition the supremum of all the smaller sums, and since all of these smaller sums are less than alpha, this means the same for beta plus delta. Throwing all of this together, we have just shown that beta plus delta is equal to alpha. As for uniqueness, I'll leave that to you. Alright, now let's deal with Euclidean division. Dividing an ordinal alpha by some positive ordinal beta means to write alpha down as beta times kappa plus delta. Kappa in this case is going to be the quotient, and delta would be the remainder. The key here is that the remainder delta has to be less than beta. To prove this claim, we proceed in a very similar way as before, but now we define a set Q of subquotients of alpha by beta. This set Q is also bounded, by alpha again, so we can take our quotient kappa to just be the supremum of Q. The proof that beta times kappa is at most alpha follows the same shape as when we were computing differences. Now that we have the quotient, how do we get the remainder? Well, we just subtract. Moreover, delta must be less than beta. Otherwise, if delta were greater than beta, then delta would be equal to beta plus some unique gamma. But then we could write alpha as beta times the successor of kappa plus gamma, and this would contradict the maximality of kappa. Now we can walk through the decimal expansion algorithm. Since the algorithm requires recursion, we will formalize the procedure by strong induction. Note first that if alpha is equal to 0, then the decimal expansion is trivial. You can just take n equals 0, and then we have an empty sum. Now we may assume for some positive ordinal alpha that we already know that all smaller ordinals have a unique decimal expansion. The first step of the algorithm is to find the largest exponent xi1 such that 10 to the xi1 is less than or equal to alpha. By now, you can probably guess how we'll find it. Let L be the set of sublogarithms of alpha in base 10. This set L is bounded by alpha, so we define xi1 to be its supremum. Using the same line of reasoning as before, you see that 10 to the xi1 must be at most alpha, as we wanted. Note that the positivity of alpha here is important, because it's impossible for 10 to the xi1 to ever be 0. Now we perform long division of alpha by 10 to the xi1. The maximality of xi1 ensures that d1 must be less than 10, and the positivity of alpha ensures that d1 must be positive. Long division also promises that the remainder rho must be strictly less than 10 to the xi1, and thus also strictly less than alpha. We can now use our strong induction hypothesis to write a decimal expansion for rho. Note that the maximality of xi1 ensures that xi1 must be strictly greater than the xi2 from rho. Therefore, we can substitute the decimal expansion for rho into our long division expansion of alpha, and this gives us a decimal expansion of alpha. With your involuntary effort to also show that this expansion is unique, this completes the proof of my claim. If you're still here, thank you for watching. If you liked what you watched, there are a couple of places where I would love for you to apply the successor function. If you didn't like what you watched, that's okay. No matter what, the set of fans that got my back will always have a well-defined minimum.